How's it going, ladies and gentlemen? My name is Kaz and welcome back to the channel. I haven't released a pure coding tutorial in way too long. According to my channel, it's been at least over a year, so this is going to be interesting. I'm sure you've read the title, but today we're going to be coding your very first kernel driver. Alongside that, we are going to code a user mode application, which will be a CS2 bunny hop cheat for educational purposes, which will use our driver to read and write process memory. That way, you don't have to use the Windows API, and it's literally going to be undetected on VAC forever, as long as VAC is user mode. The third application that you see here is just a driver mapper called kdmapper. It's a very popular application for loading unsigned drivers, which we are going to use in this video. Anyway, I'd like to actually show you what we are going to be coding in this video. So I'm going to launch CS2 and I'll get back to you. Alright, so I'm in game and I have my Epic demo for 20 open. The process of loading this cheat is going to be pretty simple. You're going to grab the driver, you're going to drop it onto kdmapper, hit yes, and as you can see, the output says success. That means it worked. The next step is to just run our user mode application. If I run that, we see attachment succeeded. That means it did connect to CS2. And basically, you can open and close this application a million times now. The driver is always going to be running until you restart your computer. Let me hop in game and show you what it does. Alright, so we are over here on Ancient, everyone's favorite map. And if I go ahead and hold down spacebar, as you can see, we just bhop ad infinitum forever. Pretty cool, and you can show all your friends. Now, just to save everyone some time, the driver that we are going to be coding in this video is going to be an IOCTL driver. Obviously, I will explain what that is later, but for people who know what that is the driver we're going to be coding. Now, before we actually get into the tutorial, I'd like to say that all of the source code from this video is going to be available to my patrons. So if you're interested in that, go ahead and sign up down below. While you're at it, I would really appreciate it if you checked out my Instagram and Twitter profiles in the description. And you might as well like and subscribe, because this is going to be a cool video. Another thing I'd like to say is that this driver is not going to bypass like other kernel anti-cheats. This driver is literally only going to bypass user mode anti-cheats. Anyway, without further ado, let's get into installing our prerequisites. Alright, so to begin, we are going to install Visual Studio. Why? Because Visual Studio is the standard way to code C++ on Windows. And of course, we're going to be using Windows in this tutorial. In order to install Visual Studio, you're going to head over to this website. Link will be down below. And you're going to go ahead and download the community version. Just hit this free download button. That should begin a download. As you can see, it's number 1 for me. That's because I've done this already. Once that's done, you're going to go ahead and run this program. And this is going to install the Visual Studio installer for you. Now, I'm not going to go ahead and do that because I already have that installed, so Visual Studio Installer. Once that's installed, it should look like this for you, except you're not going to have anything here where you see Visual Studio Community 2022 Preview. That's because I already have it installed. Instead, you should come over here to this Available tab, and you should install Visual Studio Community 2022. Now, in this video, I'm going to be using version 17.9.0 Preview 5. You are probably going to be using the normal version. The only difference between the preview and the normal version is the UI is a little bit more modern. So I'm kind of future-proofing the video because in the future, this is what Visual Studio is going to look like. But anyway, go ahead and install Community because that is the free version of Visual Studio. Once you click this install button, you should see a menu like this pop up. Right? For me, I went to modify my current installation, but for you, this should pop up by default. As I said earlier, we're going to be using C++ to program our driver and our application. So first of all, you're going to want to select desktop development with C++. Just click that checkbox. The only other thing we need to install is coming over here to individual components. What you're going to do is type in Spectre latest. And you're going to install the latest version of the Spectre mitigated libraries for your platform. In my case, I'm x64, x86. So yeah, go ahead and make sure that's installed as well. Then go ahead and close or hit the install button, whatever it is for you. And after that's installed, you should now see Visual Studio Community sitting over here. At this current time, we can build basically any C++ program, but we still can't build drivers. And that's because to code drivers, you need something called the Windows Driver Kit. Once again, link will be down below, but you're going to come over here to this website, which is the Windows Driver Kit, and they are basically going to explain exactly what I just told you, which is install Visual Studio 2022, and be sure to install the Spectre mitigations as well. After that, you're going to come here, and you're going to hit download Windows SDK, and you're going to install that. So once again, you're just going to click on that, it should download, and once that is installed, let me just go back here. you're then going to install the Windows driver kit. Now, if you are trying to code a kernel driver, you should be able to install these three things by yourself, okay? Because I'm not going to redo this for this tutorial. It's very simple. The only thing to note with install WDK is be sure at the end of the installation to select install Visual Studio extension, because that is what we want. We want the extension for Visual Studio, which will allow us to work with drivers. Once this has been installed, go ahead and open up Visual Studio. For me, once again, it's called Preview, but for you, it'll just be normal, and create a new project. And if you set your filters to C++, Windows, and you should now have driver, you should see all of these templates. If you see all of these templates, you've done it correctly, and it's time to move on. If you don't see these templates, go ahead and restart the video, start from scratch, do everything again, and hopefully it works. Okay, so now that we have Visual Studio installed with the Windows driver kit, we can code drivers. But there's still one problem. When you code a driver, if you make a programming error in the driver and your program crashes or your driver crashes, what happens is it corrupts your entire system memory, which results in a nice blue screen of death. That makes coding drivers extremely impractical. If I was constantly coding a driver on this machine, loading it into kdmapper, and then my computer's constantly blue screening, you can't realistically code anything like that. So the way to get around this is to either have a second computer or to make a virtual machine. And that's what we're going to do quickly. Once again, down below, you're going to go ahead and click on the VMware link. We're going to be using VMware inside of this tutorial, but you can use any desktop hypervisor thing that you want to use. To download VMware Workstation, you're literally just going to scroll down and you're going to click here, try Workstation 17 player for Windows. Download now. That's going to download the VMware player, and you're going to go ahead and install it by yourself once again, because you're trying to code a kernel driver. You can install things by yourself. Once VMware player is installed, you should be able to launch it, and it's going to look something like this. Obviously, I've deleted my virtual machines. That is something I will set up with you in this tutorial. But make sure your VMware looks something like this. Before we can actually create a virtual machine, we do need an operating system to create the virtual machine with. So in this video, we are going to be using Windows 11, but this tutorial should work on any version of Windows, by the way. Now, generally speaking, when you're coding drivers, you want your virtual machine and your host machine to be on the same Windows version, right? So because that means that it's guaranteed that it's going to work on both machines. But the type of driver that we're going to be coding in this video, known as an IOCTL driver, is actually very universal. It's very standard. So it actually doesn't really matter what version of Windows you're going to be testing on. What does matter though is mapping your driver. But luckily, kdmapper does work on Windows 23H2. So what I'm going to do in this video is my host machine is going to be 23H2 and my virtual machine is also going to be 23H2. If you are on the latest version of Windows, you can download a disk image directly from Microsoft for free, just like this. Go ahead and click the link in the description for the Windows download. Then you're going to come down here to download Windows 11 disk image, because we need an ISO file, which is a disk image. It's the operating system in a binary. We're going to select download Windows 11 and you're going to download now. Then you're going to choose your language, which of course is going to be English, and going to go ahead and confirm. And then this will give you a link to download for 24 hours. Just go ahead and click that. It's going to be pretty big. Mine was about 6 gigs, I believe. But yeah. Once that's downloaded, I recommend that you make a folder somewhere called VMs. And inside of that, I went ahead and I put my ISO in there. We're going to use this ISO to create a virtual machine very shortly. So let's do that. Okay, so once VMware Workstation Player is running, we're going to go ahead and click Create New Virtual Machine. We're going to use Installer Disk Image File. So that's, once again, this is the ISO that we just downloaded. So you're going to hit Browse. You're going to go and find your ISO wherever you saved it. We're going to select that and we're going to go ahead and hit Next. Now you can name it whatever you want, and I'm going to save it. I'm going to save it specifically into this VMs folder. And that's where our VM is going to be saved. So we're going to go ahead and click Next. Now we're going to select only the files needed, and we're going to make a password. It's going to be super strong, 1, 2, 3, 4, 5, 6, 7, 8. The reason it goes up to 8 is because they require 8 characters, but you can make this password whatever you want. Mine's literally just 1, 2, 3, 4, 5, 6, 7, 8, and Next. Now this is just going to depend on your computer and how good your computer is, but for me 64 works, and we're going to split the disk. Go ahead and click Next. We're not going to customize any hardware just yet, but we will later on in the next section in order to set up kernel debugging. But for now, you just leave this as default and hit Finish. This is going to go ahead and create your virtual machine. Now this is going to take some time, and if you see something like this, timeout, EFI network, don't worry, this is normal. I'm going to leave it right here. It's going to sort out its thing, it's going to do its thing, and I'll catch you guys when we are at the boot screen. Alright, so after a few minutes, you should see a menu like this. What we're going to do is click on the virtual machine, and if you use your arrow keys, you can of course navigate. We're just going to click boot normally. Hit enter and hit enter again. And as you can see, Windows 11 is now booting up. By the way, if your mouse gets stuck in the virtual machine, just hit Ctrl and Alt and you'll get your mouse back. Okay, so we now have our Windows set up. Let's go ahead and set up our Windows. Gonna hit next, install now, and that's going to go ahead and install Windows for us. Obviously, I don't have a product key. Windows 11 Home is fine, except the user license agreement. At this point, you're going to select custom install, not upgrade. You're going to install Windows onto this drive. Next. Obviously, this is going to take some time, so I will catch you guys when this is finished installing. Alright, ladies and gentlemen, it took forever, but we are now setting up Windows. So just go ahead and go through the Windows setup process. I'll catch you guys when it's done. Alright, that took forever, but we are now, we have our virtual machine up and running. The only thing I want you guys to do for now in the virtual machine is come up here to your player, click manage and install VMware tools. Then go ahead and click on this DVD drive VMware tools thing that pops up and run setup 64. The typical version is fine. Go ahead and install. Okay, cool. VMware tools has been installed. Now, as you can see, you need a restart. I'm just going to say no for now. Now I'm just going to go ahead and power off this guest because we have successfully set up our virtual machine. Alright, so at this point you should have Visual Studio installed with the Windows driver kit so we can make drivers. Alongside that you should have a virtual machine, a working one that is set up. The next step is we're going to set up our kernel debugging. That is our third requirement. If you are not interested in debugging your driver at all, then you can skip this entire section, but I highly recommend that you do set up kernel debugging because it gets very difficult to figure out problems when you can't even read messages that your driver is sending you. Anyway, to set up kernel debugging, this is going to be quite a process, so stick with me here. But to start off, we're going to open up VMware Player again. We're going to click on our virtual machine that we want to debug, and we're going to go ahead and edit virtual machine settings. Next, we're going to go over here and we're going to click add, and we're going to add a serial port. As you can see, mine is named serial port 2. Yours might be called serial port 1. I'll talk about that in a minute. Now, you're going to want to connect at power on, and for connection, we're going to change that to used named pipe. The name of the pipe that we're going to use is going to be /./pipe/com_n, but n is going to be whatever number serial port you're using. So for us, it's going to be 2. Next, this end is the server, and the other end is an application. Finally, you're going to go ahead and click on this yield CPU on poll. That's very important. And I don't know if I mentioned it, but connect on at power on is also important. After you've added all of that, you're going to go ahead and click OK, and perfect. Now you can leave this window open, but we're going to need to install a special program called WinDbg. You can type WinDbg into your search bar. You might have it already. I've got a few versions installed, but we're going to install this latest version in case you don't have it. You're going to head down to this link in the description down below, and you're just going to click download WinDbg. This is from Microsoft, obviously, and it's the newest version. You're just going to run the installer and go ahead and click, for you it'll be install, but for me it's reinstall or launch. Okay, so now that you have WinDbg installed, we're going to go ahead and we're going to launch our virtual machine again. So go ahead and click play virtual machine. Alright, cool. Once your virtual machine has booted up, if you hover over this icon over here, you should see serial port 2 using name pipe and then the name of our pipe. Make sure that that is happening. Right now we aren't debugging anything, we're still setting up the debugging. So next what we're going to do is we're going to come to the search bar and we're going to search system configuration. My virtual machine is just a little bit slow, so we need to wait a few seconds here. There we go. System configuration, and go ahead and run that. Now we're going to go to the boot tab and we're going to select our current OS and we're going to go to advanced options. What we're going to do here is we're going to turn on debug, and the debug port is going to become whatever port you chose in your virtual machine earlier. So for us, remember, we use serial port 2. Our name is COM2. If your serial port was 1, you'd use COM1. But for us, it's COM2. We're going to enable BAUD baud rate, and that's going to be 115/200. And that's about it. Go ahead and click OK, apply. And this is going to require us to restart our system again. But for now, I'm just going to exit without restart. And I'm going to come here and I'm going to direct you to your security tab. So I want you to type in security, Windows security. So before we restart our virtual machine, we're going to come here to security and we're going to disable basically every single thing we can. So go tab by tab and go ahead and disable everything. So let's go. This is where it gets quite important, because now we get into an interesting part here, which is, I believe this is called device security. You should have a tab over here called core isolation. Make sure memory integrity is off, and you might have an extra box over here, which I'll show you on my host PC quickly. Coming over here to our core isolation in the security tab, as you can see on my main PC, I also have Microsoft vulnerable driver block list. If this is there, turn that off. Make sure that that is off. Let me just turn it off quickly. I turned it on, but yeah, we keep that off. So obviously in the VM it's not here, but you will actually need to repeat all of these steps if you want to run the cheat on your main computer. You'll have to turn off all of your antivirus protections, including that potential block list, because that is going to block kdmapper, but I'll talk about that a little bit later. Anyway, we're going to continue down here, turning off everything that we can. Now you can go ahead and power off your virtual machine again. We're going to go shut this down, close it, it's good. Alright, so at this point, you should have a virtual machine which has VMware tools installed. We've also set up the debugging in the system configuration, as well as disabled every antivirus option we could find. What we need to do now is we actually need to set up our host computer for kernel debugging. Before we can actually do that, we need to check something. So what you're going to do is you're going to search for PowerShell, Windows PowerShell. You're going to right click and run as administrator. We need an elevated PowerShell for this. And we're going to check if your computer currently has secure boot on. You can check if secure boot is on by running confirm-secure boot UEFI in an administrative Windows PowerShell. As you can see, when I run it, it says false because that means my secure boot is off. If this says true for you, I need you to go and Google how to turn off secure boot for your computer, because secure boot will not let us turn on kernel debugging. But anyway, while you're here, we can now turn on kernel debugging. So we're going to do that with a simple command, bcd edit/debug on. Hit enter, and you should see this operation completed successfully. If you have secure boot, if secure boot says true, this debug on is going to fail. And once again, just to confirm, this is happening on your host PC. It's the one that runs the virtual machine. You don't do this in the virtual machine. We've already set that up. Okay, we are going to need to do one more command over here. It's going to be bcd edit/dbg settings serial debug port. And you're going to set this number to, once again, whatever number port you were using, whatever serial port. For us, it's been 2 this whole time. The name is COM2 and everything like that. For you, it might be 1, it might be 3, it doesn't matter. And we're also going to add the baud rate over here. And we're going to set that to the same number, which is 115/200. And we're just going to hit enter. Okay, so at this point, you are going to need to restart your computer. So go ahead and do that. And I'll catch you guys back here when that's done. At this point, you should have WinDbg, you should have a virtual machine that is set up to debug, and you should have set your host machine up to debug. The only thing that's left now is to actually set up the debugging in WinDbg. So let's go ahead and run WinDbg, but we're going to run it as an administrator. Click yes. We're now going to go to File, and we're going to go to Attach the kernel. You're going to select COM, and you see whatever settings I have here, we're going to copy these settings. It's going to be pipe, select that, reconnect, select that, 0 resets, the same baud rate we've been using this whole time, and the port is now going to be the full name of the pipe that we created in VMware. Let me just pull up VMware to show you as a reference. Once again, if we come to our virtual machine, we edit virtual machine settings, we go over here to our serial port, you'll see that this name needs to be the same as this name. Same baud rate, and yeah, that should be it. At this point, to test that kernel debugging works, we're going to go ahead and click OK. You should now see in WinDbg waiting for pipe COM2. If you go ahead and play your virtual machine, we should see a connection here very soon. And there we go. As you can see, we have found a connection right over here. We are connecting to the virtual machine's kernel through our host PC, through a named pipe and a serial port. Alright, at this point we know that our kernel debugging is working, at least as far as we can tell, because we can see the connection over here. So at this point, you can just go ahead and turn off your virtual machine and you can close WinDbg. Okay, so we have currently installed 3 of 4 requirements. We have Visual Studio, we have a virtual environment, we know how to debug that virtual environment. The only thing left as a requirement is kdmapper, getting the mapper that we're going to use to actually load our driver. After that, we're going to get into coding. So in order to get kdmapper, you're going to go to the description down below. You're going to click on the kdmapper link, which should take you to this GitHub repository. What you're going to do is you're going to go ahead and click download with zip on the code button. Once again, kdmapper master 1, because I already have it. After that, we're just going to click on it, and we can go ahead and extract it to our desktop for now. Of course, you put it wherever you need it to go. We're going to double click on the project and we're going to open up kdmapper.solution. Once again, you should already have Visual Studio installed, so this should not be a problem for you. Now, what you can do is you can just set this to release and go ahead and build. But I like to make a simple change to kdmapper over here in main. I would highly recommend you go through here and you just add a few standard cin.gets. You just add a few lines like this everywhere where kdmapper is going to return. The reason you want to do that is because otherwise kdmapper, it literally just closes instantly. You can't read any output. So by adding this cin.get, it's going to pause the closing of the application until you hit a button. And this is also the beauty of open source programs. We can just modify them to however we like. Anyway, once you've added all your cin.gets, we're going to go ahead and build the solution. You should be able to find a kdmapper binary by going to x64 in the kdmapper folder, release, and right there. Cool. That wraps up all of our requirements for coding this driver. Once again, we have Visual Studio, we have the Windows driver kit, we have a virtual machine to test our driver on. We also have kernel debugging set up on the host and on the virtual machine. Plus, we have a way to map our driver with kdmapper. All that's left to do now is to actually jump into coding our driver and our application. So let's do that. In this high-paced, ever-changing modern world, it can be difficult to stay up to date with new technology. Finding accurate, high-quality information for a reasonable price is almost impossible, and that's precisely why this video is sponsored by Brilliant.org. Brilliant is the best way to interactively learn maths, science, and computer science. The platform is designed to be fun and interactive, with thousands of bite-sized lessons, taking you from basics all the way to advanced topics. If you're interested in leveling up your programming game, I'd highly recommend their Introduction to Algorithms course. The lessons follow a natural linear path, which takes you from fiddling with pseudocode to understanding necessary algorithms, like binary search or bubble sort, and much, much more. So whether you're a student looking to ace your exams or a professional looking to upskill, you can try everything Brilliant has to offer free for a full 30 days by visiting brilliant.org/cazz or by clicking on the link in the description down below. The first 200 of you will get 20% off Brilliant's annual premium subscription. Thanks for listening, and let's get back to the video. Alright, how's it going, ladies and gentlemen? This is Kaz from the next day. I tried to record this segment yesterday and it utterly failed. So, it's a new day, it's a new dawn, it's time to retry. Anyway, in this segment, we're going to be coding our driver along with our user mode cheat for CS2 for educational purposes, right? So let's go ahead and get started. We're going to begin by opening up Visual Studio, of course, and we're going to create a new project. Now, when I create these user mode, kernel mode projects, I like to use a blank solution. As you can see over here, it's in my recent projects. It probably won't be in your recent projects, so you're going to have to change your filters. Just type in blank solution. You should be able to find it. We're going to create one of those. This allows us to put many projects in a single solution. It'll make more sense now. We're going to call it something. I'm going to call it sexy driver, because it's going to be very sexy, and continue. Once you've created the project, you should see Visual Studio open up. What we're going to do now is we're going to right click on the solution. We're going to go add a new project, and we're going to start off by adding our user mode project. So that's going to be a C++ project, and I like to use the empty project configuration because I don't like all of these other templates with all this boilerplate nonsense. So we're going to use an empty project next, and I'm just going to name it UM for user mode, but you can name this whatever you want. You can name it cheat, you can name it app, you can name it client, whatever you want to call it. So create. Now, I don't like using Visual Studio's filter system. If I right click on here on my project and I say add, as you see, it says new filter. A filter only exists in Visual Studio. It adds no files on your disk. So what I like to do is click on my project and then click this button here, show all files. And that makes it so that what you see in Visual Studio is actually a reflection of your disk. Once we've done that, we're going to go over here. We're going to add a new folder and we're going to call that source, right? src. And after that, we're going to add our main.cpp file into our src folder. So main.cpp. And we can just code a simple hello world application over here. Cool. Okay, so we have our simple hello world application here. Because we've added a CPP file to the project, Visual Studio can now understand that we do want to make a C++ project. Now, before we go on and add our kernel mode project, we do have some properties to change in this user mode project. So we're going to right click on the project and you're going to scroll down to properties. Make sure you have configurations set to all configurations. Make sure your platform is set to x64. We're going to change the output directory to just build like this. Solution dir build, and then we're going to change the intermediate directory to the same. So we're going to copy the build thing and we're going to change it to um_intermediates. What we're doing here is we're making it so that this user mode project will be built into a folder called build in our solution directory. So in the same directory as the .sln file, there will soon be a build file that will hold our build. Make sure to keep the configuration type as application.exe because we do want to make an exe, and we're going to change our language standard to C++20. Now, the only other thing we need to change for this tutorial is we're going to come down here to linker. We're going to go to all options and we're going to type in UAC. And this is going to be able to let us set an execution level for our program. Because we're going to be using IOCTL communication and everything like that, we are going to need to create a file, which is going to require admin privileges. So by changing UAC execution level to require administrator, what this is going to do is it's going to make it so that you have to run our program in administrator. Even when you build it, it's going to be admin. The last thing that we need to change here is we're going to come over here to C++, we're going to come over here to code generation, and where you see runtime library, we're going to change this to be MTD, multi-threaded debug. The reason we do this is because if you want to share your exe with many systems, they all need to have the same dependencies installed that our program depends on. By changing runtime library to multi-threaded debug, what the compiler is going to do is it's going to embed all the dependencies into our binary. So the size of the binary is going to be a lot bigger, but it's going to be able to run on your virtual machine. If you don't have this on, if you try and run your program on the virtual machine, it's going to give you a dependency error. It's going to say that the runtime, the Visual C runtime is not available. Anyway, after that's done, you can click OK, and we have successfully set up our user mode application for now. If you click this button, you should be able to run it. As you can see, it's asking me to restart Visual Studio because it needs us to run the program in administrator. So let's go ahead and do that. Okay, now that Visual Studio has been opened as administrator, we should be able to run it now. And as you see, sub to cazz for real, which you should do. And you should also subscribe to my Patreon, and you should check out my Instagram and Twitter down below. But that is besides the point. Now that user mode application is done, we're going to go ahead and right click on our solution again, and we're going to add our kernel mode application. It's going to be a new project once again, C++, platform Windows, project type driver, and what we're going to look for is this kernel mode driver empty. Obviously I have it under my recent projects, but you will have to go and find it. Kernel mode driver kmdf, but this is not empty. We don't want this one, we want this one. Kernel mode driver empty. Next. Once again, I'm just going to name this km, but you can name it driver, you can name it whatever your heart desires, it doesn't matter. For us, it's going to be km for kernel mode, create. Once again, Visual Studio's filter thing is happening over here, which I hate. So we're going to click on the project and we're going to click the show all files button. We're going to do a very similar thing here. We're going to go new folder, source, and we're going to add our main.cpp file. After that, we can write out our simple hello world from the kernel. So that's going to be hashtag include ntfs, and then we can just create our driver entry. And in order to print from the console, we're going to use debug messages. So we're actually going to make a little helper quickly to debug print. And in order to print, we're going to use kdprint ex. We're going to use kdprint.ex. The component is going to be a driver, the level is going to be info, and we're just going to pass in the text that we took as a parameter. One thing you do need to remember with kdprint is that you have to call this with 2 parentheses. Anyway, we're going to go ahead and debug print. All that we need to do now is just quickly set up our kernel mode properties. So right click on your project and go to properties. Once again, make sure you have all configurations and platform x64. And we're going to do something very similar where we're going to change the output to solution-dir/build. We're going to change the intermediate directory to km_intermediates. We're going to change our C++ language standard to C++20. We're then going to go over here to the C++ tab, code generation, and security check on all configurations. We're going to set that off, right? This is so that we can use kdmapper to load our driver. And after that, the only thing we need to change is in the linker. We're going to come over here to advanced, and where it says entry point, we're going to rename this to just DriverEntry and apply. Okay. At this point, you should be able to go ahead and click build solution. And if we navigate to our solution directory, you should now see a build folder. If you click on that, you should find your km.sys and your um.exe. And make sure that your um.exe does have this little administrator sign next to it. That means that you did set it up correctly. All right, so within our kernel driver project, we're going to begin by importing some functions that we need that are undocumented in NTOS kernel. The functions that we need are IOCreateDriver and mmCopyVirtualMemory. We're going to use IOCreateDriver to make our IOCTL driver compatible with kdmapper, and that'll make some more sense in a little bit. And we are going to use mmCopyVirtualMemory to implement read and write process memory inside of our driver. Now, by forward declaring these functions inside of this extern C block, this is actually going to allow us to call these undocumented Windows API functions. When I say undocumented, what do I mean? Well, there might be documentation for them out there. Undocumented just means that basically you can't call them by including things. What you have to do is you have to forward declare them, and then we can call them. This will make some more sense a bit later, but basically when you are coding drivers, you're going to come across this a lot. You're going to be importing a lot of functions that Windows doesn't necessarily want you to use. But yeah, the internet's your friend with this one. After that, we're going to go under our debug print function, and we're going to create a namespace called driver. Within that namespace, we're going to create another namespace called codes, and this is going to hold our IOCTL codes. So let's get started by creating our IOCTL codes. Alright, so here you are looking at an example IOCTL code, and I realized that I haven't even really explained what IOCTL is. IOCTL stands for Input-Output Control, and it's a very common way for drivers to communicate with user mode applications and vice versa. According to MSDN over here, user mode applications send IOCTLs to drivers by calling device IO control. So in our user mode application, we will be calling device IO control to send a structure to our driver. Then inside of our driver, we can access the structure that we sent from user mode, which is going to hold addresses, and then we can perform whatever operations we need to. Now, how do we determine what operation we're going to perform? Well, that's with the code. We create codes that represent different operations, and then inside of our IO device control, handler, we are then going to operate on the different codes. I don't know if that makes sense, but hopefully it will make some sense once we see the code. I'll explain it again. So yeah, in order to create a code, we use this macro over here, CTL code, and that basically just creates, if I hover over attach over here, it creates a constant, right? And that's why we're making it constant expression. And the name of this code is attach, and the code of this code is 0x696. Very nice number over there. All that really is important here is that we're using method buffered, right? Because our IOCTL method is going to be buffered IO, which is going to allow us to send little bits of data between both our applications at a very fast rate, which is what we want. But anyway, what you're going to do now is you're just going to copy this code that you made, and we're going to paste it 2 more times, and we're going to rename these to read and then write. And remember to increment the code by 1 every time. We can't have the same code representing 2 things. So we have 0x696, 697, 698. We have the code for attach, read, and write. We're going to call attach. We haven't made the logic for attach yet, but you can kind of imagine attach as something that we're going to implement later. This is going to basically set up our driver. Before we call read and write, which are of course read process memory and write process memory, we're going to have to call attach to attach our driver to the process that we do want to read and write process memory from. But anyway, that's it for our codes. Our codes are done. We're making them at compile time. There's a write code, a read code, and an attach code. And later on, we're also going to need to copy this and put it into our user mode application. But anyway, moving on from this, under that codes namespace, still inside of the driver namespace, we are going to create our struct that we're going to share between user mode and kernel mode. We're going to name it request, and basically this is going to hold the data that we're going to send from user mode to kernel mode and vice versa, that is going to send back to us. So let's do it. The first field is going to be of type handle, and that's going to be process ID. Then we're going to have two p voids. Then we're going to have two size_t arguments, or not arguments, fields. The first one's going to be size, and the second one is going to be return length or return size. Intuitively, process ID is going to be the process ID of whatever process we're trying to hack. Target and buffer, this has to do with mmcopy virtual machine. mmcopy virtual memory. We're going to set our target and our buffer, you know, for read and write process memory. And then this will also have to do with read and write process memory. As I said a few times, this will make more sense when you actually see it being used. So for now, we have our codes, we have our request. What we're going to do now is we're going to start setting up our driver in DriverEntry. Alright, so in DriverEntry, what I've done here is I've created a Unicode string called driver name, and I've called RTL init Unicode string. So one thing you need to understand about the kernel is that when functions want strings, they typically don't want a const char pointer, you know, a const character pointer. What they want is a p Unicode string or a Unicode string pointer. And in order to create a Unicode string, what we do is we just declare it, and then we call RTL init Unicode string, and it's going to place this string into the structure, and then we can go ahead and use it. Now, one thing I need to explain is that since we are mapping this driver with kdmapper, this introduces a few problems. Usually DriverEntry has parameters. Over here on MSDN, as you can see, this is what DriverEntry usually looks like. It usually takes a p driver object, and a p Unicode string registry path. As you can see in our DriverEntry, I have left out these parameters. The reason I've left them out is because they are going to be equal to null anyway. They're not supposed to be null, but because we're using kdmapper, which manually maps the driver, that means that the operating system doesn't even really know that the driver is running. So the operating system can't give the driver what it usually expects, which would be these two parameters over here, driver object and registry path. Usually you don't even need driver object and registry path, so it's not a problem. But we want to make an IOCTL driver. And in order to create the IOCTL communication, we need this driver object. But as I just said, we don't have it. I mean, we can declare it over here. I can write it out, but it's going to be equal to null, so there's no point. In order to get around this problem, we actually have to kind of springboard from this entry point into a new entry point that kind of simulates the actual entry point. Okay, I just said entry point like 5 times. This will make some more sense right now when I type it out for you. We're going to create a new function called entstatus, sorry, it's not called entstatus, of type entstatus. That's what it's going to return, and it's going to be called driver main. Or you could call it DriverEntry or whatever you want to call it. And this function is now going to take the expected parameters. So it's going to be a p driver object. We're going to call it driver object, and it's going to be a p Unicode string, of course named if I could spell, registry path. And by default, we can just return status success like we did in our original entry point. When we load our driver with kdmapper is going to call DriverEntry. And that's obviously going to print whatever message you put here. That's going to create our driver name, and then we just need to add one more line of code here, which is going to be return IO create driver, which is, if you scroll up to the top of your project, it's this function over here. It's this undocumented NTOS kernel function that we have imported into our project. We're going to call that function, and we're going to pass in the address of our driver name, and then we're going to pass in the address of our driver main, our new main function. And we need to pass the address of that like so. This now becomes our real entry point, driver main, because what's going to happen is we're calling IO create driver, which is going to populate these two parameters correctly for us. We're going to have a valid driver object. We're going to have a valid registry path. But one thing we can instantly do is we can use unreferenced parameter on registry path, because we are not going to be using that. And when you are coding kernel drivers, by default warnings are treated as errors. Of course you can turn it off, but it's not a good idea to turn it off. Obviously we're not using driver object, but we are going to use it. We never use registry path, so it wouldn't let us compile if we haven't used something and we don't explicitly say it's unreferenced. Anyway, we can now go ahead and get started coding our driver main. One thing I did not mention that I just realized is our driver name over here. It has to be \\driver \\/ and then the name of your driver. But this name can be whatever you want it to be, right? So in this video, we're going to be using sexy driver. And just, make sure you spell the name correctly and everything, because we are going to be typing it out about 2 or 3 more times. So anyway, let's go. What we need to do now is we actually need to create the driver's device. So let's do that. We're going to start by creating another Unicode string called device name, and we're going to put \\/ device and then your driver's name into that string. We're now going to use this string to actually create our device object, like so. Alright, so what I've done here is obviously I created the device name, then I created an empty device object, or not empty, but it's set to null, and then we call IOCreateDevice. Earlier we called IOCreateDriver, now we call IOCreateDevice, passing in our driver object, which we needed. This is the whole reason we called IOCreateDriver, because we needed our driver object over here, passing in our device name and our device object, which it populates. Then what we do is we just check the status to make sure that it is successful. So if status is not equal to status success, we print and then we return the status, whatever the problem was. And if all goes well, we can go ahead and debug print that it was successful, like so. Driver device successfully created. By the way, I forgot my new line over here. You just need a new line in your driver entry under your debug print. Back over here to our driver main, our real entry point, quote unquote. What we need to do next is we need to create a symbolic link. So that's going to be very similar. Go ahead and follow along. Once again, we are going to create a string for the 3rd time, and we're going to populate that with DOS devices and then your driver name. So once again, DOS devices, driver name. The previous one was device, driver name, and the very first one was driver and then driver name. Anyway, once that's done, we can now create the symbolic link like so. We can create our symbolic link by calling IOCreateSymbolicLink, passing in the name of the symbolic link along with the device name. And then we, of course, just make sure that it is status success. If it's not equal to status success, we print the error message and then we return the status once again. At this point, we just want to quickly log that it did succeed. So I'm going to copy this one above and I'm going to say driver device. I'm going to change this to driver symbolic link successfully. And I'm going to change creator to established. Cool. At this point, we are actually almost done. We still have a little bit to go, but what we start doing now is actually setting up the IOCTL communication. So let's go ahead and do that. We're going to begin by setting a flag that's going to allow us to do buffered IO. Next, what we need to do is set up the handlers for our driver object. So the driver object has a bunch of major functions that are going to get called by the operating system, and we need to set up functions that are going to handle those calls. So think of it kind of like an event handler thing going on here. Now, in order to do this, we actually do need to create the functions. So what we're going to do quickly is you're going to put a pin in whatever we're doing here. Just keep in mind that we still need to come and do stuff down here. But we're going to come up to the top to our driver namespace under your request structure, and we're going to create 3 functions like this. First one's going to be called enttyStatusCreate, and it's going to take 2 parameters. All of these functions are going to take the exact same parameters because, yeah, they all have the same, signature. Each one of these functions is going to return enttyStatus. It's going to take a pDevice object and a pIRP. IRP stands for IO request packet. That is what carries the data between our IOCTL communications. This function, we can actually fully code it. It's going to be very simple. We're just going to call unreferenced parameter device object because we never use that in this function. What we then do is every time you do complete an IRP, every time you do complete an incoming request packets request, you have to call IO complete request like so. And we are just going to pass in our IRP, and then we're going to pass in IO no increment, just like that. And then what we can do is just return IRP dash, sorry, not dash, IO status. and then dot status. And this is basically it's a structure that holds the status of the function that just happened, so that the operating system and the user can actually tell what happens when these handlers are called. Anyway, so that's our create one. Now you can go ahead and copy this one. By the way, copying and pasting code is really bad because you make a lot of stupid mistakes. But this one, we're going to rename this to close, and it's literally going to be the exact same thing. That's why we copy and pasted it. But now we are going to copy this one more time, or you didn't even need to copy it. You can just paste again. And we're going to rename this to device control. And this one is going to get a little bit more complex, but we are not going to implement that just yet. So let's just leave a note here, note to do, because yeah, we need to come back, and this will be the last thing that we need to code before our driver is done. So we're just going to finish the few lines that we need to do down here in driver main, and then we just need to come and code our device control, and everything will be good. So coming back down over here, now that we've established our handler functions, we're going to come down to our driver main, and we're going to set them. So that is done like so. We're going to access the major function array, and we're going to index it with irp mj create, and we're going to set that equal to driver create. Okay. So what's happening here is within our driver object, there is this, as you can see, it's the size 28. There's this array called major function. And what's going to happen is when things happen and when events happen on our driver, it's going to go through and it's going to call the functions that are saved inside of this array. So in order to make our driver do what we want it to do, we actually have to set our own functions inside of this major function array. So we're going to go ahead and copy this two more times. We're only going to set three functions. That's going to be create, it's going to be close, and it's going to be driver control, the three functions that we just made. But what's the problem here? Device control. Not driver control, device control. And we just need to change the things over here to correspond. So this is going to become close, RP MJ close, and then this is going to become device control. And just like that, we have now set up the handlers for our driver. All that is left to do inside of this function is to go ahead and clear the flag, clear a special flag, which I will talk about in a moment. We're going to go ahead and clear the do device initializing flag because we have completed initializing our device. It is done. It is initialized. And after that, I'm going to go ahead and just debug print one more time. And what we should do is we should return status, not status success. We should return status. Okay, so as I said earlier, this is all done. The only thing we have left to do is to fill in our logic in device control. So what's going to happen is, remember earlier when I was talking about our IOCTL stuff, you have to call device IO control in order to send a message from user mode to kernel mode. When you do call device IO control, what's going to happen is it's whatever you put into it is going to come through on this function. It's going to come through this function. The IRP is going to hold our data that we send through device IO control in the user mode. We need to come and implement our logic in here. So for example, our read and write process memory and our attach. We need to implement these logics, lots of logics, attach, read and write. So let's go ahead and get started with that. What I'm going to do first of all, is I'm going to debug print, and I'm just going to say in here, we're going to make a plus sign because it's not an error, and we're going to say, so if you ever see this message, you know that at least your IO is working, at least your device control is working. But yeah, we'll go ahead and debug this in a little bit when we are done coding our driver and we've made a simple application. We will go ahead and debug this in our virtual machine to make sure everything is working nicely. But yeah, anyway, device control. We're going to start off by creating NT status, call it status like usual, and we're going to set it to actually status unsuccessful to begin with, right? So by default, it's going to be unsuccessful. Now, what we need to do is we need to get the stack location of the IRP. So why we need this is because this is going to hold which code we are passing, and we can get it like so. By calling IO_get_current_IRP stack location, we can get our current IRP stack location. And as I said earlier, we need this to determine which code was passed through. So this is going to hold which control code, so either attach, read, or write, whichever one here, we are going to, it's going to hold that. But you'll see it'll make more sense now. The other thing we need is the actual request struct that we sent from the user mode. So we can do that like so. So we can get the request object by accessing IRP associated IRP.system buffer. If we actually go to the definition and look at this, we can see that associated IRP is a union, and system buffer is obviously the third thing in this union. So what it says here is this operation is being buffered and the field is the address of the system space buffer, which is exactly what we want. What does this operation is being buffered mean? Well, earlier inside of our real main, is it real main? Yes, it is real main. We set the flag do buffered IO, which is what we want. And then also when we create our codes, as you can see, we create our codes with a method buffered, right? To say that we do want to buffer these codes. So that is just how we access the buffer. Because we're using buffered IO, it is in system buffer in that union, which is called associated IRP. Anyway, what we're going to do now is we're just going to make sure that none of these are null, because if they null, our computer is going to fucking blue screen, and we hate those things. So now, every time you want to return out of one of these IOCTL handlers, you do have to call IO complete request on the IRP, which we did do in these other two, which we just need these to be defined. We don't have to do anything in them. But like here, we're going to call IO complete request, and then we're just going to return the status, right? Because we haven't even changed status yet. It's still unsuccessful. So it's going to return unsuccessful, which is what we want. Okay, now what we're going to do is we're going to create a static pointer to an E process. And we're going to call that target process equals null pointer. Now, obviously, this is a static variable, which means that basically it's not going to be remade every time the function runs. This is going to exist. It's going to have a value that exists beyond the lifetime of this function. Naturally, this is going to be the target process that we want to read and write memory to and from. We're just storing it in here for now, but it will make some more sense in just a moment. What we need to do now is we need to create const u_long, and we're going to call that control code. So this is going to be the code that we passed in from user mode. And as I said, we access that from the stack IRP. We go stack IRP parameters dot device IO control dot IO control code, just like that. And now using this control code, we can create a switch statement, and we're going to switch on that control code. The cases are now going to be the codes that we defined over here inside of this codes namespace. So the first case is going to be codes attach, and we can just break for now. The second one is going to be case codes read, break, and then the third one is going to be codes write, and then break, and then I just need the case statement over here. Now we can actually implement the read and the write process memory and the attach. So what attach is going to do is it's just going to set this value to a valid program, right? Because obviously it's null pointer by default. So that's going to be pretty simple. It's going to be status equals ps lookup process by ID, and the process ID that we're going to use is going to be within that request struct that we're passing in from user mode. So it's going to be request process ID, and the target process that we want is going to be the address of target process. If I could spell it correctly, target process, like that. Cool. And then obviously it's going to break out. Once it does that, it's going to complete the request, and it's going to return IRP status like this. We actually will, okay, I'll come back. We'll change that in a moment. Let's just continue here. That's literally it for attach. All that's going to do is it's going to populate this target process with an actual process. Theoretically, that's going to be CS2 in this video, and our driver is going to hold a handle to the E process of CS2. And then we're going to use that with copy virtual memory, because if we come up here and we take a look, it needs a source and it needs a target pointed to an E process. So yeah, let's go ahead and implement our read process memory. The first thing we need to do, obviously, is we need to check if target process is not equal to null pointer, because if target process is a null pointer, we're going to blue screen. And then what we do is we just say status equals copy virtual memory, not copy memory, copy virtual memory. And yeah, have fun typing this out. Okay, so our read process memory logic is as follows. We're going to make sure that target is not a null pointer, and then we're going to call copy virtual memory, with our source process being the target, right? That's where we want to get our data from. The source address is going to be the target address, the address that we put into target, which this will make sense when we code the user mode side of things, because we're going to put the address that we want to find into target. And then once again, it wants a target process, which is going to be the current process. It's going to be our driver, because we're going to be reading from the driver. And then of course, we're going to store the value in buffer. And then it just needs a size, kernel mode, and blah, 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 blah. So what we can do is we can actually just copy this function. And once again, be careful with copy pasting functions, make sure you know what you're doing. Now what we need to do is we basically just need to switch around the processes, and then we need to switch around the target and the buffer. So what I mean is literally we're going to take ps get current process, we're going to replace it with target process, and then we're going to place target process where get current process was, and then we're just going to replace target with buffer, and then replace target with buffer like that. So as you can see, target buffer, buffer target, target process, ps get current process, ps get current process, target process. They like reversed because we're using the same function to read and write. We just have to reverse these things. Okay, cool. So after that, what we do now is before we IO complete request, we just have to set some information in the IRP. And after that, we'll be completely done with our driver. So we're going to go IRP, IO request packet. We're going to use the arrow to dereference the object or whatever it does. IOStatus dot status equals the current status, just like that. And then we're going to say IRP IOStatus once again dot information equals size of request. And then at the very end, we're just going to return status like that. And that should theoretically be our driver done. So what we're going to do now is we're just going to code a simple user mode application that attaches to Notepad. And then we're going to launch our virtual machine and we're going to debug our driver to make sure that everything is going correctly. After that, we will code our CS2 cheat and then you'll be on your way. All right, so let's get started with coding a basic user mode implementation of using this driver. Obviously, you're going to come to your user mode application, and then we're going to need kind of two like boilerplate functions. And I'm really not going to code these because I did these in my very first video on this channel, which is how to code external CSGO bunny hop. The functions that I'm talking about is or are get process ID and get module base address. So these are just not working right now because I need to include windows.h. And then after that, we need to include TL help 32. And after that, they work. But I'm going to show you what this code is and I'll explain what it does. Let me zoom out here so that you can go ahead and copy it. That's the whole function over there. Hopefully you can see it. But what this function does is it's going to create a snapshot with th32cs snap process, null being the thread process ID over here. And that's basically going to create a snapshot of all the processes on the system. We're then going to create an entry. We're then going to loop through all of the entries inside of the snapshot. And we're going to wide string compare to see if it's equal to process name. If it is equal to process name, we're going to return the process ID of said process. The next function is going to be get module base, which is literally the exact same thing, except instead of using snap process, let me zoom out so you can see the whole function once again, and you can go ahead and copy that. Oh, I just hit my mic. Probably pause the video and go ahead and copy it down. But what this function is going to do is it's going to do the exact same thing. It's going to create a snapshot, but this time of the modules inside of the process by process ID. So we're first going to get the process ID, then we're going to call this function passing in the process ID, which is going to create a snapshot of all the modules in the process by process ID. We're then going to loop through them, and then we're going to call wide string substring to see if it's in the module, and if it is, we're going to return the module base. Very, very straightforward stuff over here. And once again, I explain this in a lot more depth. We actually code this together in my very first video on this channel. Anyone who's been in the hacking community knows these two functions like the back of their hand. Everything else I will be coding with you. So once you do have those two functions down, once you've got them, we can move on. We can move on to a little bit more copy pasting because we're going to come back to our actual driver. And let me zoom out a bit. What we're going to copy is we're going to copy everything from the bottom of this request struct to the top of namespace driver. So we're just going to copy driver, codes, and then request like this. Just to zoom out again to show you exactly what we're copying. It's just namespace driver, namespace codes, and request. We're going to come back into our user mode application. We're going to paste that, and we are just missing a bracket at the bottom here, like that. There we go. Okay, so as I explained earlier with the control codes, we are going to need the exact same control codes inside of our user mode application. That's why we copy pasted them. And then we are also going to need the very same struct called request. Now, you can change the names of these variables, but you have to make sure that the size and the order is exactly the same because it is expecting a 40 byte structure to be shared between both the user mode and the kernel. Now, in our driver, in this driver namespace, we implemented our handlers for the logic of the driver. But in the user mode application, what we're going to do here is we're going to implement our attach to process, our read process memory, and our write process memory as standalone functions inside of this namespace. We're going to set up our whole driver framework. By the way, obviously in this video, I'm putting everything inside of the same, everything's going in main.cpp in both projects. You probably don't want to do it this way because if you're making a serious project, it's going to get really cluttered and crazy. It would be a good idea to go ahead and take probably this driver namespace and throw it into its own, source and header files. Consider it anti-paste. That's your job. Okay, so we're going to begin by coding our attach to process function, or our attach function. That's going to look something like this. We're going to make a bool attach to process, and it's going to expect a const d word of process ID. Let me zoom in here. It's also going to expect a handle, and we're going to call that driver handle. Now, every one of these functions that we're going to code, or the other two functions, the read and the write process memory, are also going to expect a driver handle. So it might actually be a good idea to put this into a class, and then that way you don't always have to pass the driver handle. But in this video, we're coding this functional style with dependency injection. So let's go. Anyway, attach the process. We're going to create the request struct, just R, and we're very specifically not going to initialize it. So usually when you make variables, you want to give them an initial value, but request, we're not going to initialize it because the thing is, if you do initialize it, that's going to take a few extra CPU cycles, and we are hackers and we are lazy and we want performance. And therefore, we are just not going to initialize it. But what we are going to initialize is the process ID field of this request structure. So we're going to reinterpret cast this to a handle. Remember, the reason we have to do this is because we declared it as a handle. Well, cazz, why the hell did we declare it as a handle when it's a D word, The reason we did that is because over here, no, not that one. Where's it? Because PS lookup process by ID wants the process ID as a handle. So, I mean, either we could make the process ID a D word inside of this request struct. It could be a D word, but then we'd have to cast inside the driver, or we can just cast here. It doesn't really matter. That's actually up to you. So we're going to cast that D word into a handle, and we're going to store that in process ID. And then to actually send that through to the driver, we're going to say return, and we just call device IO control, like I told you earlier. Over here, we call device IO control, this function over here, to send a control code directly to a specified driver, causing the corresponding device to perform the corresponding operation. That is exactly what we want to do. So we're going to call device IO control, and this takes quite a few parameters. The first one is going to be our driver handle. The next one is going to be the control code that corresponds to this function. So this is going to, of course, be our attach code. So codes attach. After that, we're going to pass the address of our request. We're then going to pass the size of our request. We're then going to pass the address of our request again, and we're going to pass the size of our request again. And then after that, we're just going to pass null pointer and then null pointer. Like so. Yeah, so to send the message through to our driver, we're just going to return device IO control, passing in the driver handle, the code is attached. We're going to pass the address of R, the size of R, the address of R, the size of R, and then null pointer, null pointer. Size of R is, of course, 40 UL, which is correct because our request is 40 bytes. Cool. That actually is it for our attach to process. But while we're here, we might as well implement our read and write process memory. So that's going to be a little bit more complex, but it's still going to be pretty easy. We're going to create a template over here, class T, and it's going to return T, of course, because we are read process memorying. We're just going to call it read memory, and then this is going to take, of course, handle driver handle first, and then it's going to take a const standard uint pointer underscore T of address, just like that. Then what we are going to do is we are going to create T temp equals nothing, so we're going to initialize temp to 0. We're then going to create our request, and we are not going to initialize our request. We're then going to go r.target equals reinterpret cast to a p void address, just like that, but we didn't call it address, we called it adder. So we're going to set the target to our address, and as I said earlier in the video, because over here inside of our driver, if we come over here to the read process memory, it takes a source process, a source address going to be the target, and then it takes the target address is going to be the buffer. So our target address is going to be the address we want to find, and then the driver is going to put the result into the buffer, right? So the buffer is going to be equal to the address of our temp variable. So that means that the driver is directly going to put the result of that copy virtual memory call into this variable right here, into temp, because we are passing in the address of temp. And then r.size is going to be equal to size of the template parameter. And after that, we just need to call IO device control exactly how we did the last time. So I'm just going to copy and paste it, but we're not returning this time because instead of returning a Boolean, we are going to be returning the temp value, which, as I said, the driver, we are passing the address of this temp value through the buffer to the driver. And what the driver is going to do is it's going to populate this, because right now we're setting it to nothing. It's going to populate this variable with a value. We're going to then return that value. And that is read process memory done. Now it's time for write process memory. It's going to be very similar. Template class T. This time it's going to return void. So it's not going to return anything. We're going to call it write memory. And this time it's going to take 3 parameters instead of 2. So it's going to be driver handle. It's going to be the same const standard UN pointer address. But this time it's also going to take a const T reference value, which of course is going to be the value that we're going to be writing. Now, instead of creating a ttemp like we did in the last one, we're just going to go directly into filling in our request struct. R.target is going to be exactly the same. It's going to be the address, but we do need to reinterpret cast the address because it expects a p void, but we take a UN pointer. R.buffer is going to be equal to the value this time, but we can't just set it to value. That's not going to work. So we actually have to set it to @value, and then we have to use a C style cast over here, which I hate, because I like using C++ cast, but we have to do C style because this is undefined behavior according to C++. It'll give us an error if we try to reinterpret cast that. But what's happening here is we're passing this as a reference, right? And what happens when you pass a reference is when you use the address of operator on a reference, it literally just returns the address of the very thing itself. Actually, now that I think about it, we might actually just be able to do it like this. I'll test that later, but for now, we're going to leave p void and then we're going to cast the address of value to a p void. And then, of course, don't forget to set your size to the very same thing, size of, not size underscore t, size of t. And then we just need to go ahead and return device, call device IO control, and we don't return anything. Now, one thing that I did fuck up here, which is absolutely horrible, is this is why you don't want to copy paste code, because I haven't updated the code that we use. As you can see, all of these are using the exact same code, which is wrong. Just remember to come to your read memory and change the code to read, and then come to your write memory and change the code to write. And basically, we have fully completed our driver framework inside of our user mode application. All we have to do now is implement it. But before we code the CS2 cheat, what we're going to do is we're going to code a simple application that just connects to Notepad. We're going to run that in our virtual machine. We're going to debug it, and we're going to make sure that everything is working. So let's go ahead and do that. We're going to start by trying to get the process ID of Notepad, like so. Okay, so we're going to start by getting the process ID of Notepad. And obviously, if it's equal to 0, that means it failed. We're going to say failed to find Notepad, and then we're just going to leave. Now here is where it gets important. We're going to create the handle that we need to call our driver functions, right? Because all we're missing is this parameter over here. So in order to populate driver handle, we need to create a handle to our driver. And we're going to use our driver's name for this, but it's going to be like this. So const handle, and I'm just going to call it driver, but obviously it's the driver handle, is equal to create file, like so. Over here, you're going to give 4 backslashes with a dot, 2 backslashes, and then the name of your driver that you've been setting inside of your driver, inside of the actual driver project, whatever you named it in all these places, you're going to use that exact same name inside of this user mode application. That is the name of your driver. We're going to open it with generic read. There we go. So we're going to create our driver handle using create file, the name of our driver, generic read, and all this other bullshit. And that is going to return us a handle to our driver. What we just need to do now is we need to make sure that this handle is valid, and we can do that like so. So we're going to check if driver is equal to invalid handle value. If it is, we're going to see out an error, and then we're just going to see in to pause execution. At this point, we can call close handle just preemptively to driver, because we don't really want to leak the handle to our driver. But above that is now where it gets a little bit more fun. So now what we're going to do is we're going to try and attach to Notepad using our driver. So that's going to be like so. We're going to go driver, attach to process, and we're going to pass in Notepad's process ID. Sorry, we're going to pass in our driver handle first, and then we're going to pass in Notepad's process ID, and we're going to check if this is equal to true. If it is equal to true, we're going to see out attachment successful. And that's all we are going to do for now. Although what we should do is add a standard sin.get to the bottom here. So theoretically, this application is going to open. It should search for notepad. If it finds notepad, it should create a handle to our driver. If that succeeds, it's going to try and attach to our driver, which means that it's going to set this internal static target process value over here inside of our driver. It's going to set that to a value instead of null pointer, and that should be notepad. And eventually it's going to be CS2 at the end of this video. But for now, you should be able to go ahead and build solution. As you can see, for me, 2 succeeded. It's now time to launch our virtual machine and start and check out if it's working. So let's go ahead and do that. Alright, ladies and gentlemen, I'm here on my desktop. I have VMware open, and I also have my build folder open inside of my sexy driver, along with kdmapper over here. You might want to grab that out of your kdmapper folder, out of your build. All we need to do right now is launch WinDbg. So we're going to go ahead and right click, run as administrator. Remember, you have to run it in an elevated mode to connect to the kernel. We're going to go file, and we're going to go attach the kernel. Once again, these are going to be your settings. They shouldn't really change very often, and you're going to go ahead and click OK. And it's going to wait for our connection. Now all that's left to do is to go ahead and launch our virtual machine. Go ahead and hit play, and I'll catch you guys when my VM is up and running. Once again, just make sure that you are, of course, getting a connection over here. As you can see, kernel debugger connection established. And yeah, once again, I'll see you guys now. Alright, ladies and gentlemen, my virtual machine has successfully started. Now I'm going to go to the search tab, and I'm going to go to the security tab, because unfortunately Windows will, every time you restart your virtual machine, it will re-enable real-time protection. So damn, this virtual machine is slow, but basically we just need to disable that quickly. In your security tab, you're going to go to virus and threat protection, manage settings, and turn off. Earlier you should have turned off every other setting when I asked you to. If you haven't, then go ahead and do that now, because that will mess with loading your driver. The next thing that we need to do is we need to get our driver, kdmapper, and our user mode application on this virtual machine. So how do we do that? Well, earlier in the beginning of the video, I asked you to install VMware tools, and what that allows us to do is literally just drag and drop things into our virtual machine. So there we go. We've got kdmapper. You need km.sys or whatever you named your driver, and then you also need a um.exe. Now, if you are struggling to, if you aren't able to drag and drop things into your virtual machine, then you either didn't install VMware tools, or it is struggling, it's just not working. So you're going to come up here to player, you're going to go manage, and you're going to reinstall VMware tools. Okay, now that we have all our stuff on here, there is one last thing that we have to do. In order to see kernel debug messages that are printed from kdprint, oh yeah, by the way, make sure that you did build in debug mode, because kdprint is only going to print when you compile in debug. Okay, but besides that, every time you want to use WinDbg to see debug messages, you're going to have to click the break button, which is going to pause execution on the virtual machine. You'll see here, it just freezes. You can't really access anything on there. And what we're going to do is we're going to type in a command. As you can see, it says KD, that means kernel debugger. It's waiting for a command. The command we're going to type is ed for edit, nt, !kd, ihv driver mask, and we're going to set that to 8. Now, why are we doing that? Well, if you remember, inside of our driver, we have debug print, and we're calling kdprint.ex, which once again only works if you build in debug. So you're not going to see any messages if you don't build in debug. But anyway, that's also why I called it debug print. But kdprint.ex, as you can see, the first argument that it takes is actually a component ID, and we are using ihv driver, and we are using info level, which is level 3. So what we are doing here is we are typing in this command. We are editing the ih driver mask to 8. Okay, because right now it's 0, and I don't actually know what number this should be for info level, I'll be honest, but 8 works, so we're going to make it 8. Now, this is extremely annoying because you have to do this every single time, basically every single time WinDbg restarts, or even every time kernel debugging restarts, you have to do this. You have to break, you have to type this in. The alternative to this is inside of your virtual machine, you're going to go into a registry editor, and then you're going to add a key. I'll leave a link to in the description down below on how to do that. You should go ahead and do that. It's just, but for this video, for the sake of simplicity, we're just going to use this command to edit kd ihv driver mask. So if you hit enter, there we go. It has, if it pops up, that means it's been done. And now remember, you still can't use the virtual machine because it's still paused. You either have to click this button to go, or you can just type G in the command, hit G, and now we are back in action. So at this point, theoretically speaking, if we run our driver, if we drop it into kdmapper, we should go ahead and see its output. So let's do that. We're going to load our driver. Yes. And there we go. So our kdmapper output ended with success. That's always good. And if we check out the kernel debugger, we see sub to cazz from the kernel, driver device successfully created, driver symbolic link successfully established, and driver initialized successfully. That's what we like to see. But there is one more thing that we do want to see. If we come back to our driver, inside of device control, we did add a debug print message here, device control called. We do want to make sure that this is being called. And the only way to see this message is to call device control. And how do we do that? Well, we need to use a command from our user mode application. And in this case, it's going to be attached process, right? By calling attached process, we are calling device IO control, which is going into the kernel. It's going into our driver device control. But this user mode application that we have set up is looking for notepad, just for an example, because we don't have CS2 installed on our virtual machine. We're looking for notepad. So let's go ahead and launch notepad. And if we run our user mode application, what we should expect to see is a few messages from the user mode application, but we should also expect to see a very nice message from here. We should expect to see device control called inside of our kernel debugger. So let's go ahead and see if all goes well. So once again, notepad is running. We're going to go ahead and run user mode. Yes. Attachment successful, device control called. That is a very good sign. That means that at the very, very least, our device control is working. We are able to communicate with our driver. Now, we still haven't tested if read and write process memory work. We're going to find out if those work in the next segment of this video when we actually code our CS2 cheat. But for now, that is just an example of how you would debug something on the kernel, in the kernel on your virtual machine. But anyway, you can go ahead and close out of your virtual machine and everything like that. Now it is time to code our CS2 bunny hop. All right, ladies and gentlemen, before we can code our CS2 cheat, we actually need to get offsets for the cheat, right? We all know what offsets are. We all hate them equally. So in order to get that, we're going to go to the internet and you're going to click on the link to A2X's CS2 dumper, which should take you to this GitHub repository. And I don't know what just happened to my GitHub. Let me refresh over here. So what we're going to do here is we just need two files. We're going to come over here to generate it and we're going to find client.dll.hpp. I'm going to open that in a new tab and then I'm going to look for offsets.hpp, just like that. We're going to go ahead and we're going to download both of these files. So you can click download raw file like that, and then download raw file like that. Cool. Once that's done, they should be in your downloads folder. You're going to want to navigate to your driver folder, and then we're going to go into the user mode project of our driver folder. Then we're going to go into the source directory of our user mode project, and then we're going to go ahead and we're going to drag and drop these into our source directory next to main, just like that. Now, if we return back to Visual Studio, go ahead and click on user mode on your profile, on your project, and click this refresh button, and you should now see client.dll.hpp as well as offsets.hpp. What we're going to do is we're going to right click and we are going to include in project and do the same for offsets.hpp, include in project. Now we can go back to main, we can scroll right to the top and we can go ahead and we can include both of those files. So first we're going to include client.dll.hpp, then we are going to include offsets.hpp. Now we can come back to our main file and we are going to be working inside of this if statement, if driver attached to process. But before we do that, we need to go to the top here and we need to change our get process ID from notepad.exe to cs2.exe. And then we're going to update our error code over here. It's from saying failed to find notepad. It's going to say failed to find CS2. Still going to create our driver in the exact same way. And we're still going to try and attach. So we're going to say, going to keep this attachment successful message, but we're just going to add a body to our if statement over here. And inside here is where we are going to code our bunny hop cheat. To begin with, we do need to get the address of client.dll, which is a module. That is why we have this function over here, get module base, which I did show you how to code earlier and in other videos. So that is going to look something like this. We're going to say if const standard uint pointer. We're going to call it client is equal to get module base, and we are going to pass in process ID, of course, and we're going to pass in client.dll. I'm going to add a semicolon. This is some new C++ syntax. Well, it's not new. It's not exactly new, but we're going to say client not equal to 0. So what we've done here is we've actually declared the client variable inside of this if statement. This is the actual if check. This is just like a normal statement, as if it was outside of the if statement. But anyway, that is for a C++ tutorial later on. Inside of this if statement, we will have a valid client, which is always a good sign. So, I mean, we can go ahead and print that out. We can say client found, like that, something like that, just to let us know what's happening. Afterwards, we are going to enter an infinite while loop. So while true, and then we can just add a break condition to this. So something like if get async key state vk underscore end. If you press end, we're just going to break out of this. But otherwise, we're going to be inside of this infinite while loop going on and on and on. So the first thing we need to do, as per usual, is we need to get our local player. Now, CS2 has changed a little bit. We no longer get our local player. We now get our local player pawn. So that's going to be something like this. Const auto local player pawn is going to be equal to driver, and then we're going to call read memory from our driver. And what we're reading is going to be a standard uint pointer underscore t, because we do want, it will be a pointer, so we do want to use an 8-byte type. And what we're going to pass in is driver, because we need to pass in our driver handle first. It's going to be client plus client underscore DLL, the namespace client underscore DLL, and what we're going to get is DW local player pawn. So the final thing should look something like this. What we're then going to do is we're just going to check if local player pawn equals 0. We're going to continue, right? So that means that if for some reason we fail to get our local player, we're just going to continue and do it again and again and again. We're going to skip. After we have successfully got our local player, what we need now is to get our local player's flags, right? Because the flags will tell us if we're on ground or in the air and whatnot. So pretty simple. Once again, const auto, we're just going to call it flags, is going to be equal to driver read memory. This time we're going to be reading a standard uint32. We're not going to be reading a uint pointer because this time we want a 4-byte unsigned int. We're going to pass in driver, and we're going to add, instead of client plus an offset, this time it's going to be local player pawn plus c underscore base entity. So we just got to find base entity over there, and the offset from base entity is going to be m underscore f flags. So this will be your final line over here. Flags is equal to read memory. We're reading a uint32, passing in driver, local player pawn, plus the flags offset. Now we can create a few bools. So we can say const in air is equal to flags. And then we use this, we use a bit mask thingy going on. One smaller than 0 or whatever. And sorry, this needs to be a boolean. Const boolean in air. So is your player in air? That's what this is. And then we're also going to create a const bool space pressed equals get async key state vk underscore space. The last variable that we need over here is going to be a const auto, and it's just going to be the current value of force jump. So we're going to say force jump is going to be equal to, just going to copy this read memory over here because it's going to be reading a uint32 as well. So we're going to be reading a D word over here from force jump. So let's actually just name a D word. It doesn't really matter. And yeah, so we're just going to store the value of force jump. Okay, now we can actually start our bunny hop logic. So if space pressed and in air, so if you're in the air and spacebar is pressed, what we're going to do is we're going to call driver write memory, and this time you don't actually have to give a type into the template because it'll automatically deduce what type we are passing in. So driver, and then the address is going to be, of course, client plus client underscore DLL DW force jump. Oh, and I just realized that I just made a horrific error. We're reading force jump up here. I don't know why I used, you see, this is why you mustn't copy paste code. We need client plus force jump up here. My bad, sorry about that. So driver, client plus force jump, and then we're going to write this to a very interesting value of 65537. Okay, now if you want to know how this works, go ahead and watch someone else's video. I'm not explaining how this works. We are just using this to implement our driver to make sure that the driver does work. So else if space pressed once again and exclamation in S, so the opposite. So if we are on the ground and space is pressed, we are going to copy this line. Once again, don't copy lines, very bad, but do copy this line. So we're going to change this to 256, and then the last else if is going to be if space isn't pressed and force jump is equal to 65337. We just need the double equal sign there. What we're going to do is we're going to copy this line. We're going to write 256. And the only thing I'm missing here is we just want to sleep this for about 5 milliseconds before we do decide to write to our force jump. And yeah, after that, theoretically speaking, we should be good. We should now have a fully working CS2 bunny hop. So let's go ahead and test it out. We're going to build in debug. I'm going to launch the game and I will catch you guys there. All right, ladies and gentlemen, I am in the menu of CS2. We're going to go ahead and we're going to manual map my driver on my host PC, and we have success. And then we're just going to go ahead and run our user mode application where we found client. Attachment seems successful. So let's hop into a practice game. I hate ancients, so let's go with like overpass. That's fine. I'm going to select CT. And if I hold down spacebar, we bhop. And this is obviously kernel bhop. We are not reading and writing process memory through RPM and all that crap. This is through the kernel. Boom. Boom, boom. Look, I can even do it backwards. Anyway, ladies and gentlemen, I really do hope that you enjoyed the video. It's been a very long video and it's taken me a long time to make. I hope that you did manage to get a working driver out of it, and I hope that this doesn't completely and utterly ruin CS2. But anyway, this was just meant to be an introduction to kernel development. If you want to get better now and you want to go and bypass other kernel anti-cheats, I'd recommend you study kdmapper and see how kdmapper maps the driver. I'd also recommend that you go and study different communication methods, learn about their pros and their cons, and then also you're just going to need to go and reverse engineer those anti-cheats that you want to get around to discover how they detect you and how you can get around them. But anyway, ladies and gentlemen, I hope you did enjoy the video, and as always, shout out to the following sexy patrons. You guys are awesome, and check out my Instagram and Twitter down below, and leave any comments or suggestions or whatever in the description down below. I'm tired, I'm over this video, it's time to go edit. Hope you guys have a good one. Cheers and peace out.